Hi, so welcome to this presentation. Thank you for coming. I know it's a little bit a topic a little bit different from everything that we normally have at KubeCon, but yeah, I wanted to see how it would go. So this talk is about hardware in the loop testing with Kubernetes. So first, yeah, I want to clarify what I mean with hardware in the loop. So hardware in the loop is the technique or sometimes art of testing with hardware in your life cycle to make sure that your software is being tested with the final hardware or at least a subset of that hardware in your lab. And the idea is that you simulate part of the environment or to make sure that you can reproduce something that works. So in companies where I've been where there is no hardware in the loop testing, this is how it looks. So maybe you have different variants of your devices, and when you are going to make a release of your firmware, you need to test it on all of them and make sure that everything is fine, do lots of manual testing, and that doesn't scale well. And without a good testing strategy, we all know what happens. You know all the first ones, so stuff that used to work doesn't work anymore. It's difficult to figure out what's really happening. You cannot meet your deadlines. But in the case of hardware and the physical world, sometimes it's even worse. Something could explode or crash or, well, yeah. So in the software industry, we have this very well figured out. We have a good landscape of options that we can use to make sure that everything is under control at every point of the development process. But what happens with hardware? Hardware is not as easy to manage as VMs, containers. Normally, you don't have out-of-band management. Sometimes you have, but it's very rare. And you have tons of different interfaces, like canvases, video inputs, video outputs, human interfaces. There are many options. I would like to ask to the audience if in your company, do you build anything with embedded devices? Okay, nice. And do you already have any kind of hardware in the loop testing? Okay, and are you happy with what you have? Okay, okay, nice. So, so let me tell you about our project and what we have been working on. The name of the project is Jumpstarter, and we started it in emerging technologies at Red Hat, and now we have a small community of contributors. We have an automotive OEM. They don't want to be named yet. We have the Red Hat automotive team and the original team from emerging technologies. First, you see a lot of automotive in there. We don't want this project to be only automotive. This is something that, yeah, we are really trying to be careful about. So the goal of this project is to enable open source hardware in the loop testing from the developer desk at the start to later on, being able to build a lab where you have your devices in racks and you can connect all the interfaces that you need and use drivers to get to those interfaces, but you also can use that as a developer, but also connect it to CI/CD, which is the most important part of that talk. So if you see that arrow, it goes down to the typical diagram. And the idea is that the framework and the service is really open, so you can connect it to anything. Tekton, GitLab, runners, GitHub runners, Jenkins, and anything. It's really, as long as you put the credentials in the secrets, it's being able to access the service and run your tests. But OK, I'm a developer, and this sounds too complex. So you can start with something like this. You have the Jumpstarter framework and client. It's written in Python. I will explain why later. Well, this part is written in Python, but the server-side part is written in Go because it works much better with the Kubernetes ecosystem. So if you're a developer, you can write your configuration to define the interfaces to your device and then use it locally the same way that you will use it in a remote lab. So, OK, I'm done with that. I know it's working, and now we are growing. We are bringing this into our lab. So you can move into something like this. So the same configuration that you were using as a developer, you can now put it into what we call Sidekick servers sometime. It's just a Linux device that has to be side by side with your hardware and that has the physical interfaces to that hardware. And that same configuration that you had as a local developer, you just put it on the exporter, run this as a service, and add an endpoint and a token to connect it to the controller. And everything else is the same. So from the developer point of view, when you are connecting remotely, this is how it would look if you are going to use the command line options, which is just an option. Is some of the drivers have the ability to export command line actions. So the first line is requesting a shell for a selector of hardware, and if that hardware is available, you are going to be connected to that hardware, and you will have access to those commands with the J command, which is completely dynamic. So depending on the drivers that you have, you will see some commands or other commands. But you can also use it from Python. So all the drivers provide a client side that allow you to perform activities on the hardware. Like in this case, we are using the client and there's a connection to flash an image into the device, power it on, and then we keep capturing a video snapshot. It's a very small example. OK, so yeah, can I connect this to my CI/CD system? So it's the same thing. The CI/CD system can. We have more actions, and I will show an example later. But you can do the same thing. You can write your tests in Python and take your device through the life cycle that you want, and provide the results of your tests. Eventually, we also want to add support for, well, you could do it now, but it's not very predictable, to testing with several devices at the same time. Maybe sometimes your test is going to involve several devices that are working together. So eventually, you could do that. And this is, if you are writing tests, we also provide some helpers for PyTest so far, but we are open to any other frameworks. And this is an example of testing. So if abstracts the part of getting a client, and you can just use it. So in this example, we are just, the first test is going to boot a Linux device with a serial port, make sure that it can log in. And the next test is going to take a video frame and compare it to a snapshot that we have on the repository with some degree of freedom. You can configure that. And then it's going to interact with the console to make sure that you have specific devices. For example, we use this for testing that the NVIDIA Orin device drivers work, and that the GPU is working, that we can run inference, and so on. It's one of our internal use cases. And this is how an exporter configuration looks like. This is like the first part, which is defining the endpoint token and the name and namespace where this exporter is available on the cluster. And then we have this export part. This export part is going to, it's defining like the different interfaces that you have to the hardware. In this case, we have a storage device that we can control for the device. We have a power interface that is connected to an SNMP PDU. We have a serial connection and a video input. But we have lots of drivers, and we are growing that. And we are happy to accept contributions. And the framework is super open. You can write, you don't even need to make your drivers public. So we have like an example repository that you can clone and make your own driver. Every driver has a exporter like close to the hardware side and close to the client side. We are starting to have drivers to do some level of virtual hardware also, because people was requesting that. But yeah, we have a lot of future ideas and open to other ideas. And I don't know if you can see that on the screen, well, more or less. This is how a driver looks like. Every driver is composed of a server side. That is what you configure on the exporter service, and a client side. I think I don't have time to go through the details, but it's very easy to write a driver. And OK, let's get into the demo side of things. I hope everything works well. Let me first explain what I have deployed in Kubernetes together with Jumpstarter. So in this demo, I wanted to put together like a complete development environment on the cloud. So we are using Eclipse Che and the dev spaces operator. We are using Tekton for the pipelines. Dex is in charge of the authentication. And we use GitLab in the cloud for our repositories. And then we have two exporters. Those exporters are actually running on Madrid on my home office. I will show it later. And there you have the deployment configuration for what you will see. So you can reproduce this. There are some instructions. I have tested it to some degree. If you try it and something fails, please ping me. I will try to help. So this is how it looks. Please don't mind the don't look too much at the dust, because we were doing renovations just before that picture. And yeah, I tried to get rid of it, but yeah, it is what it is. So I just tried to make like a very simple example. In this case, so we have two exporters. One of them has a Raspberry Pi Pico, a Debug Pro, and a camera that is pointing to the device. The other one one of them is working as a Debug Pro too, the device, and then a logic analyzer, but I didn't have time to finish the driver for the logic analyzer. But the idea is that you could use a logic analyzer connected and take traces and check the traces if you want. So, OK, I'm going to open this dev space here, I already started it because it normally takes like a minute or so to start the first time. And if we go into this desk space, so you can see it comes from this GitLab repository. We have this. Okay, so this is Eclipse Che, and we have our development environment in here. The example is written in Rust. It's just from the Raspberry Pi Foundation examples with Rust, and we can build it with Cargo. We can yeah, I can show you. Is the font size okay, or so like, yeah, okay. Make it just a little bit bigger, just in case. So in this workspace, I configured a couple of sorry, I think I moved my mic. A couple of client credentials. Those are on the cluster. If we look here, those are configured as secrets. And every time you start the workspace, Eclipse Che is going to mount those secrets for you. So I have, this is like the kubeconfigs in Kubernetes. That is going to give me access to the hardware available on my lab. So if I do GMP get exporters, I will get the available exporters in this Jumpstarter controller, and I can request some of that hardware. For example, if I do GMP shell and I will use the webcam true selector, so this is going to ask the controller for a lease for some time. It will expire in 30 minutes, but you can request more or less, and we have like role-based access control that you can define and define like the limits of that. So when I connect, I'm now connected to this exporter. I can use the J command, and I have like the drivers that I configured. I can show you the configuration of that that exporter that looks like this. You will see it's what you see on the J command. So you have the J, you have the probe driver for the using the probe RS tool, which is a flasher debugger tool, and I provide the serial number of the debug probe. I have a serial port pointed by ID, so I'm always sure that it's going to pick the right one. And then I have a video output that is pointing to the webcam device. So what I see here on the other side, it's just that. The video interface doesn't have a CLI yet. Eventually, yeah, we want to add it, but yeah, we didn't have the time. So now, in here, I can do things like, for example, sleep. I will give it 3 seconds, reset, and then in parallel, serial start console. So this is going to start the console very quickly, and then in the background, it will wait 3 seconds and reset the device. So, okay, this is the device running, and I can interact with the device remotely. It's a very silly example, and you can use the other commands. Every command has subcommands. So in this case, the probe has download, erase, info. You can read from memory if you want. But if I do a jprobe info, I can see what's connected to the debug probe in this case. But I mean, the most interesting part is that you can interact and build your tests in Python. So I will start with a small example. It's still not a test, but it's a video. This one is a video stream like the one that I had on the slides. That is going to be writing a JPEG file. It's like a Pulseman video transmission, thanks to VS Code and Eclipse Che, it's working. So, and I can stop it anytime. For example, if my session, my lease ends or I disconnect, I lose access to this connection and any driver, any stream that it's being connected. But we also have some tests that we wrote for this example. So I like to use the PyTest framework with hardware because it executes the tests in the written order. And that's helpful because hardware tends to be stateful and it's quicker to iterate. So you don't need to bring everything from the start to end for every single test. It's not so deterministic, but it's faster. So this example is first testing the probe connection. So okay, I'm just checking. I have an ARM device connected to my probe. The next test is going to download my binary file that Rust compiled. And then the next test is going to interact with the serial console, reset the device, and look for this hello KubeCon output. And the next test is going to, check that the regular word write is working, then checking that the DMA word write is working, and then interacting with the device a little bit. And then we have some tests for the LEDs, so making sure that the LEDs are blinking, and then the next test is checking that the LEDs are blinking in opposite directions. So if I run PyTest here inside my connection, it's going through all those tests, checking that everything works. We can also open the video here and see what the test is seeing or how it's looking for the LEDs in this case. Okay, so all the tests passed. But yeah, now let's exit the console. The list is released, and this hardware is again available for users in the cluster. So let me show you the cluster side of this. So in this demo, this is what we deployed on the Kubernetes cluster. If you are going to use Jumpstarter, you only need this deployment, nothing else so far. If you want to, I wanted to make it nice and so how it could integrate with the other projects, like the Eclipse Che, Tekton Pipelines, and so on. So that's everything else. But you only need this one. It's very thin. And you get a few CRDs on the cluster. For example, you have the exporters. So you can see the exporters are registered on the cluster, and you can label them. You can create new ones and get credentials for them, and it's very easy. You can also see the Jumpstarter clients on the system, and you can also see the leases that have been going on the cluster. So who used what and when. Um, we will need to improve that in the future, like do cleanup and start moving it maybe to a database, because that's a lot to put on CRDs. And on the long term, I think that will not work, but yeah, we will be working on that. The idea of this is that eventually you can also figure out the usage of the platform, who is using what, how much. Maybe you need more hardware of one type or less hardware of one type, or even eventually assign cost to the usage of the hardware. So I want to show you, in this case, the connection to Tekton. So I defined a pipeline run here that is using several tasks. So we have a task for getting a list from Jumpstarter, releasing it, running commands, and well, I have a git clone because I had to tweak it. So yeah, I will not get into the details of this, but I can show you how it works. So let me do it, fetch all. So I'm going to break, make a breaking change. So we have those LEDs that are alternating in intensity. So I'm going to put them non-alternating, and that should trigger failure in the test, because it's one of the things that we are checking. So if I do git commit, and I push it, I can create a merge request. Yes. And yeah, we see this is blocked until the tests will pass, and that triggers the pipeline in Tekton. You could, I mean, also use the GitLab runners as well, but I just wanted to show how it integrates with Tekton too. So if we go to Tekton, we will see that, yeah, it's fetching the repository, then it will build the binary, request Jumpstarter for a list of the specific hardware that we need. Here in the details, yeah, I think we can see it later. It has the selector for the hardware that we want. And then you can, after that list, you can perform several actions, and then the cleanup is a release of that list. So the hardware is back on the cluster, and another job can use it, or another developer can use it. And yeah, let me I will leave that running. I'm just running out of time, so let me go to the takeaways. So yeah, with Jumpstarter, you can build hardware. You can use it as a hardware in the loop framework. You can create a whole software factory in Kubernetes if you want. And Jumpstarter is an open source project. The drivers can be on the project, contributed to the project itself, or you can have your own drivers anywhere. The architecture is really simple. And also wanted to, you have this on the slide. So we run this parallel community to Jumpstarter about hardware in the loop. So if you are interested in this topic, please join our meetings. We talk about this all the time. And finally, yeah, some links to our repository, our Matrix channel, and That's it. Thank you very much for coming. I don't know if we have any time for questions. I think we don't, but I will be available. What? Sorry? What? Oh, yeah, let me open. It should have failed because we broke it. So let's see. Thank you. That was a good question. So yeah, it failed. And it should have failed, yeah, in the, sorry, the font is too tiny. Yeah, but it was failing on the test opposite LED cycles. So it just detected that they are not alternating. And if we go back to, yeah, to GitLab, OK, it failed.